Hi everyone, thanks for joining us today for Build Smarter Gravity and Gabion Wall Analysis with the LimitState GEO. I'm Tom Pritchard and I'm Principal Engineer here at LimitState. I'm joined by today's speaker, who is Colin Smith, the LimitState GEO Product Manager. The webinar is going to last about 30 minutes and we'll hopefully have a few minutes at the end for questions, which you can post at any time in the interface in front of you. And for any questions that we don't manage to get around to answering live, then we will always follow up via email in the next few days with a reply for you. We'll also be making a recording of the session available on our YouTube channel, details of which I'll mention at the end of the session. So without further delay, I'd like to pass you over to Colin Smith, the LimitState GEO Product Manager.
Okay, well, thank you, Tom. Welcome to this, our sixth LimitState webinar of 2021. And today we'll be looking at gravity and Gabion wall analysis with LimitState GEO. I'll just stop my video to avoid distractions. There we go. And give you a brief introduction. So as it's a short presentation, main aim is to give you a flavor of what the software can do and focus on a few specific features. There won't be time to get into the details of all the software functionality, but there will be time at the end for questions. So before we get into looking at Gabion walls and gravity walls, just a little background on the technology. If you examine standard textbooks and design codes, you see a broad consensus on the general principles of retaining wall analysis, which are adapted for specific scenarios. So typically a limit equilibrium approach is used. An analysis may be based on either a Rankine earth pressure distribution or a Coulomb wedge type analysis. And LimitState GEO is essentially an enhanced wedge type analysis. So if we go to this page, you can see a number of retaining wall analyses, and essentially the software is capable of modeling thousands of wedges in order to get a very accurate solution to any collapse problem. Now, just a little bit of background to the technology used in LimitState GEO. We use a method called discontinuity layout optimization, or DLO, which is a systematic automated method of identifying critical slipline patterns. This was published in the Proceedings of the Royal Society back in 2007, and essentially poses a problem as a large but simple linear optimization problem. So the steps very briefly are, we have a problem domain here. It's just a rectangle with a load at the surface and a fixed boundaries to the left and to the base. We then populate the domain with nodes rather than elements, and we, in principle, connect every node to every other node for potential slipline. We then use optimization to pick out from that set of roughly 60 sliplines, in this particular case, the 6 sliplines that form the critical slipline mechanism for this very simple scenario. And that's displayed in this final diagram D. Now, with modern optimizers, we can solve problems with millions of potential sliplines very rapidly, and this is essentially what LimitState GEO does. So it's able to model with thousands of nodes, millions of potential sliplines, and the more nodes, the more potential sliplines you have, the closer to the collapse mechanism you're going to get. And the method has been verified against a wide range of benchmark problems. So just say a little bit about reviewing the principles of ultimate limit state design before we start looking at the retaining wall problems. Ultimate limit state is a hypothetical state that should never really arise in practice. And design codes such as Eurocode 7 aim to ensure the probability of this ultimate limit state occurring is very low through the application of partial factors. So in order to undertake a ULS analysis, we have to drive the system to collapse by some means. It just won't happen on its own. And this is essentially what we're doing in the software. And you can do this implicitly or explicitly. In many conventional analyses, the process is implicit, but in a general numerical analysis, such as used in LimitState GEO, it must be done explicitly. So we have two possibilities. First one is posing the question, how much bigger does a load in the system have to be to cause collapse? Or by what factor A does this load need to be increased to cause collapse? And in the software, this factor A is called the adequacy factor on load. The other way of looking at the problem is asking the software, how much smaller does the strength of the soil need to be to cause collapse, or by what factor F does the soil strength need to be reduced to cause collapse? And this factor F is the adequacy factor on strength. So those are the kind of core principles. We'll come back to those in a moment. But if the adequacy factor is greater than or equal to 1, then essentially the system is stable, the system is modeled, and if it's less than 1, the system is modeled is unstable. And in general, this adequacy factor will correspond to a global factor of safety or over-design factor if you've already applied partial factors. So on to gravity and Gabion wall analysis. So for gravity wall analysis, conventionally, codes tend to ask you to verify that it's stable against sliding, overturning, bearing capacity, and a global failure. And so this is essentially a check of 3 or 4 different failure modes out of what is essentially an infinite number of modes. With LimitState GEO, there's no need to carry out these separate checks. The software, in effect, will check all of them and will find the critical mechanism. So it'll check all 3 or 4 of these failure modes, plus many, many thousands of others, and it will pick out the most critical ones. So in this mechanism on the right, we've got a mixture of a sort of bearing failure, a sliding failure, and an overturning failure. And that's the most critical one for that particular scenario that's modeled. We come to Gabion wall analysis. Of course, we have to do the same standard gravity wall checks, but we also need to check for stability in all the interfaces between the Gabions. So that adds complexity for hand calculations. And again, we'll be concerned about sliding, rotation, and possibly crushing of the Gabions, particularly at the corners of the Gabions. And of course, these types of checks also would apply to masonry retaining walls. So with LimitState GEO, again, there's no need to carry out separate checks of all these additional failure modes. The software will find the critical mechanism. So we'll look at how that's done in the software. So when you start up the software, this is the sort of screen that you get. And what I'm going to do is click on this new project button, and what I'm going to do is use one of the built-in wizards. So the software can model any geometry you care to draw. You can import geometries from DXX files and so on, but it also has a number of wizards in it to build standard problems quickly, so that you can explore the behavior of these systems quite quickly. So I'm going to click on the Gabion wall wizard. I'm going to skip entering general details there. I'm going to modify some of the built-in parameters just to give us the type of wall that I want to use. I'm going to have 6 Gabions in this particular case. And I'm going to leave everything else as the default, so the default materials and so on. There isn't time to sort of talk about these in detail, but you can set properties of the soil, the wall material, surface surcharges, and so on. So I'm just going to go through all of that and click finish, and that builds me a model. So I've got a stack of 6 Gabions, the existing soil body, some backfill, and a surface surcharge. Now, just looking at the layout of the software, on the left, we have a number of buttons that control drawing or the geometry of the problem. So we'll come back to those a little later. Here, we have what's called a Materials Explorer, and these are the materials that are used in the problem. So, for example, this soil A, which is also this material here, if I click on that, on the right, we have a thing called a property editor. So anything I click on, its properties appear on the right. And this soil, we can see has a unit weight of 20. It always behaves in an undrained manner, so it's always going to use its undrained shear strength CU of 25 kilonewtons per meter squared. Equally well, we have below the geometry editor, we have below the property editor, I should say, we have a geometry editor. So again, anything I click on here, the geometry of those blocks appear down there. And across the top, we have various buttons for controlling the display, but also solving the problem. Now, just looking at the way the problem is built, we'll just look at some of these gabions. So the gabion itself is a block. I've got the geometry down here, and if I click on that, its properties appear up here. I won't explain all of the properties, but if I click on the material here, we're basically modeling gabions as rigid blocks, so they won't fail internally, with a unit weight of 24 kilonewtons per meter cubed. Critically, on the interface of the gabions, between two gabions, we have two materials modeled, one called a Morcullo material, one called a cutoff material. We'll come back to those later on, but they essentially allow the gabions to slide or rotate or crush at the corners. We also have materials between the gabion and the soil body, which are interface materials, which allow us to model weaker strength along the interface than in the main soil body. So for example, this material is modeling a strength on C in tan 5, 1/2 of its parent material, and its parent material is this soil C material, which is that color and is in fact that material. So it's basically modeling half the strength of the adjacent soil. So you can set that to any value you like. It could be anything from 0 to 100% of the strength of the adjacent material. So that's how we're modeling the Gabion wall. And as I said earlier, we're trying to model this situation at its ultimate limit state. We have to drive it to collapse by some means. A very useful feature in the software is a diagnostics tool. I won't go through all the details, but at the top, it tells us that adequacy is being applied to these bodies. So that's set up by the wizard. So it's actually set to the self-weight of that solid that's just highlighted, self-weight of that, and also this surcharge. So we're basically asking the question, how much bigger does the backfill weight and the surcharge have to get to cause collapse? So I'm going to click solve. So to solve the problem, I just click this button. And it quickly finds the failure mechanism. I can animate that to help me understand that it's basically sliding on the base of the Gabion rule system. And I've got an adequacy factor here of 1.11. If I click on that, that just tells me that the unit weight of soil block 1 was 20, specified as 20, has to be increased to 22.22 to cause collapse. And likewise, these other quantities have to be increased by a factor of 1.11 to cause collapse. Now, the software will model failure on any interface, so we can force it to fail on this interface here simply by increasing the strength of this block of soil. So again, in the property editor, its properties appear. It's currently got a undrained shear strength of 50. I'm going to set that to 500, so very strong. And now the bottom block will not fail, and the top block is going to slide. And my adequacy factor here has gone up because I've constrained the problem. It's finding it harder to get it to fail, so it's gone up to 1.63. And again, that is the weight, that the factor we have to increase the backfill weight by to cause collapse. I can also pose the question in an alternative way, as I mentioned earlier, factor strength. In this case, software is asked, how much do we have to reduce the strength by in the soil to cause collapse? It takes a little longer to solve because that's to iterate to get to that solution, but it comes up with an answer of 1.56. And essentially that means that we have the initial values as specified in the problem, and they have to be divided by 1.56 to cause collapse. So we've still got a decent margin of safety on that particular design. And while there isn't time to look at that at the moment, we can put in partial factors to pre-factor, in a sense, all the parameters before we do the analysis to give us that extra margin of safety. Okay, so what I said was I was going to just explain a little bit more about how those Gabion interfaces are modeled. So here I've got a model of just 2 Gabion blocks. And if we look at the Gabion material, again, it's rigid and it's got a unit weight of 24. And the geometry, if we look down here, it's basically a 1x1 cube. So each block is going to weigh 24 kilonewtons. So at the moment, what I'm going to do is just apply a unit load to the surface. So again, I click on the right, this value here in the property editor, it's a unit load and I've got adequacy true. So I'm just asking the software, how much bigger do I have to make that load to cause collapse? So if I click solve, what happens? Well, basically I push the 2 Gabions into the soil, I get a bearing capacity failure. I've set this soil strength to be very high, so I get a very high value. But that's what I'm not trying to demonstrate here. What I want to do is look at these interfaces. So currently we've got no interface material here. So the interface just takes on the property of the adjacent material, which is rigid. So it cannot do anything. Now, while we're interested in sliding mainly of these Gabions, we're actually going to start looking at vertical loads for reasons which will become obvious in a moment. So we have 2 materials in the wizard model that I showed you earlier. These 2 materials here, what's called an interface cutoff material and a more cooler material. We'll start with the interface cutoff material. I can take that material, I can use drag and drop to drop it wherever I want. I'm going to drop it on that interface. That interface now has that cutoff material on it. And if I click on that, look at its properties, it says it will limit the compressive strength or compressive stresses on that boundary to 1000 kPa and the tensile stresses to 50. So if I then press solve, I get an answer of 976. This time, effectively, the block moves down. It's crushing or failing by crushing the top surface here. And what it's having to do is it's having to overcome this compressive strength of 1000. So we've got a force on the top of the block of 976. We have to add the weight of the block, which is 24. That gives us 1000, and it fails that way. If I flip the load round, so make it -1, and then solve, then I get an answer of 74. And the block fails by basically in tension coming apart. And the load of 74 is what I should expect. On the interface, I've got a tensile strength of 50. Now, normally we're not going to expect much of a tensile strength between blocks, but here it's modeled at 50 at the moment. So I've got to overcome that. So that's a 50, and then I've got to add on the weight of the block. There's 24, so that gives me the 74. So that just illustrates the broad principle of how these interface cutoff materials work. We'll come back to those in a moment. So I'm going to take the load off here, and I'm now going to put on a horizontal load on the side, which we're kind of more interested in for retaining wall purposes. And if I solve that, what I get is a rotational failure. So it's rotating as a rigid block. Because we have the ability to fail in tension or in compression, a gap can open up. We get a collapse load of 68, which is not necessarily quite what we might expect. And the reason for that, I can click on this body and I can actually see the distribution of stresses along here. I'm generating a lot of tensile stress here, which I wouldn't normally expect, and compressive stress here. So what I'm going to do is modify the material properties and take away the tensile strength. and then resolve, and I get an answer of 24. And I'm pivoting essentially around the corner there. So this is what I'd expect. If we do a moment calculation, the weight of the block is 24. It's a 1-by-1 block, so actually the force required to cause it to rotate is going to be 24. And if I click there, we get no stresses on this boundary, and here we're actually got quite a high stress just at the very corner to allow it to rotate. Now, the useful thing about this material is if I reduce this strength to say 100, its compressive strength to 100, then I can use that to model crushing. So if I animate that again, you can see now that I'm not rotating about the corner, I'm rotating it about a point further in. And if I click on that body, you can see that I'm actually mobilizing 100 kPa, certainly at this edge here. And so effectively I'm modeling crushing at that point. So that allows me to give a bit more richness to the modeling, if you like, and model that sort of corner crushing, which can happen for certain Gabion types, certain masonry blocks. So that gives me the ability to rotate. What I'm going to do is just return that strength to 1000 so we get rotation in the corner, and add in this material. Now this is a more Coulomb material. It has an angle of friction of 26.565. I've chosen that angle because tan of that angle is 1/2, so that makes it a nice round number. I'm going to drag and drop that onto that interface, and I'm going to add, we can have more than one material on an interface, so I've got simultaneously this frictional material and the cutoff material, so I can now model sliding failure as well as rotational failure. If I click solve, what happens is I get sliding, and I get a load of 12, which is what I expect. The weight of the block is 24, multiplied by tan phi is 1/2, I get 12 is the required load to cause that to slide. So that's as I expect. But the software is still able to model rotation. If I increase the friction angle to say 45 degrees, then the force required to make it slide is actually bigger than the force required to make it rotate, and it will revert to the rotational mode. So it'll always pick the most critical mode. Okay, so that's a quick run through of that interface material. And so if we go back to my original Gabion model, and let me just check I've got this soil property set correctly. If I resolve that, actually I meant to solve that with factor load mode, just for speed. So I'm going to revert to factor load, resolve that. So we basically stop the bottom block from sliding by making this base layer strong, and we've got an adequacy factor of 1.63. We get a sliding failure. Now, in order to illustrate the other modes of failure, what I can do, as I did before, is with this frictional material, which basically is on the interface of every block. So you can see on every one of those interfaces, we've got that black and brown banding, and these materials are appearing here. I can access the properties either this way or direct from the property editor. The angle of friction is 35 at the moment. I'm going to set it to 45. So that makes all the interfaces have an angle of friction of 45 because they all use the same material. And if I solve, the mechanism looks the same, but when I animate, you can see that I'm actually getting rotational failures in the failure mode. And the adequacy factor has gone up because I've made the interface strength stronger, but the failure mode has changed. It's easier to fail by rotation. Now you can see that there is quite a bit of crushing going on at the edges in this case. So I can suppress that by making this 5000, for example, very high strength, and solve again. And actually that reverts us back to a sliding mode. So that crushing does allow that rotational failure. We're back to sliding essentially, but the adequacy factor has gone up because again, we've made the system stronger. So we can obviously play around, explore the influence of different parameters here. And also, I haven't really illustrated it, but we can explore the difference in changing, for example, geometry of blocks. So I can make these blocks bigger, doing this rather crudely, and see what effect that has. It's very easy to do. Change the solution. And my adequacy factor goes up to 2.3, so I've got an even bigger margin of safety in that case. And that one is also failing by sliding. And finally, of course, we've been focusing very much on failure in the wall. If the base soil was very weak, I'm going to reduce its strength down to 25 here, then the software will hopefully find a global sort of failure where we've got failure underneath the wall, and effectively the wall is staying intact and the soil is failing around the wall. Okay, so that hopefully gives you an insight in the flexibility of the software. We'll just revert back to the PowerPoint to wrap up. So in summary, hopefully I've shown you that the analysis of LimitState GEO uses similar principles and mechanics as in conventional limit equilibrium methods, but we can handle complex geometries and kinematics. There's no need to consider different failure modes, such as sliding and toppling. Essentially, the method automatically searches all possible failure modes every time you solve. Hopefully, you've seen it's very interactive. It solves quickly, so it's very easy to ask what-if type questions and give you a better feel for the problem. Also, I've shown you a number of features. This diagram here, I thought it'd be useful just to show a different type of retaining wall, a sheet pile wall rather than a gravity wall, but the principles are the same. You can apply surface loads anywhere you like. You can have variable backfill geometry, including slopes. We can model tension cracks. We can model properties on the wall interfaces, reduced interface friction or cohesion. Tension cracks, of course, are also modeled when you get rigid body rotation of Gabion blocks. I didn't illustrate it, but you can model their soils. And again, I didn't illustrate it, but you can put in water tables and measure water, look at the influence of water pressures. Okay, so that wraps up today's webinar. Just a little bit of time for questions. So please, if you have any questions, do put them into the question and answer dialogue in the webinar. So I've got a question, how do we use this with the Eurocode? So I mentioned that earlier. So at the moment, when I do an analysis here, I'm just going to revert this strength back to very high. I'm not applying any partial factors. And so if I click on my solution here, it's telling me that I have a characteristic value that's the same as the design value. Very easy to apply partial factors. So for example, if I want to apply Eurocode Design Approach 1 Combination 2 factors, I just select this in what's called the Scenario Manager. That then pre-factors unfavorable loads according to these factors, favorable loads according to these factors, and the material properties, of course, get reduced. So I click OK on that. Those are automatically applied. If I resolve, then I get a fairly similar failure mechanism on sliding as well, but the adequacy factor has gone down. It's gone down from 2.35 to 1.59, and that's because I've got these Eurocode factors applied. And if I click on the solution, you can see that here in terms of the loads, of course, factoring permanent actions, which is a unit weight of the soil, they don't get factored. The factor is 1, but this variable load is unfavorable. It has a characteristic value of 5. It gets factored by 1.3 first, and then over and above that, the adequacy factor is applied to get collapse. So as long as that adequacy factor is bigger than 1, then essentially we have satisfied the equation that actions are less than resistances. Okay, I think we're out of time there. So I'll just flip back to the webinar and just pass over to Tom to wrap up.
Thanks, Colin. Thanks everyone for attending. I think we've got a couple of questions that I said at the beginning. If we didn't get around to them, then we'll answer you by email in the next couple of days. Also, as mentioned at the beginning of the webinar, we'll be uploading a recording of this webinar to our YouTube channel in the next few days. And that also includes a number of other webinars and applications of LimitState GEO. So yeah, please do feel free to take a look. For more information on LimitState GEO, you can visit our website or send us an email or follow us on LinkedIn or Twitter. And finally, we'll be running some more webinars throughout 2022. And as normal, we'll send out event notifications via email in advance of those, as well as advertising them via the website and on social media. So again, thank you all for listening. Do have a great festive period, and I hope that you can join us again for one of the future sessions. Goodbye.